Hey, good morning.
Good morning. How are you?
Yeah, I'm fine. How are you?
Doing great. Thanks for joining.
Good to hear. Let's see.
Hi
Hey,
there.
Stefan.
Hey, Stefan.
See you.
We have a full hour, right? It looks like it's scheduled for an hour.
Yeah, if you don't need an hour, we can make it shorter. It's up to you.
Okay. I plan to talk for 40 minutes about and 20
That
minutes
sounds
for
good.
questions. Great.
That
Okay.
sounds good.
Cool.
Right.
Should I wait longer before I get started since it's just us three?
Let's just wait for a few people to join, right?
Okay, welcome Ian. I made you host officially, so you have full controls to start, stop, pause, or anything you need to do. It's exciting that you are here to talk about your grant and how it worked.
Thank you, Amanda. And it's good to meet you virtually. So let me share my screen. I'll start. Let's see. So I'm gonna try to enter presenter mode here. I'm not sure. Can you see all the slides in the full screen?
Yep, perfect.
Great. Awesome. So I guess I'll go ahead and get started. My name is Ian Dardick, and I'm a PhD student at Carnegie Mellon University. And I'm very excited to talk to you all today about our work on fully compositional inductive invariant inference in TLA+. This is a research project I've been working on for over a year now with my advisor, Professor Enso Kang, who's actually on the call as well. And this project is funded by a grant from the TLA Plus Foundation. So thank you very much to Amanda and the whole TLA Plus Foundation for funding this work and making this possible. So I'm going to start by offering a scenario that I think will resonate with many people here on this call. So you make a TLA plus specification, we'll call it spec, and you want to show that it's correct. So you pass it to the TLC model checker, and then you wait. and then you wait some more. And in fact, if it's an infinite state protocol, you are going to be waiting forever. And to make matters even worse, you might have a constant in your specification. And the TLC model checker, of course, can only take finite instances, but in general, our constants might be unbound. So you can only use TLC to check finitely many instances. So TLC is a great tool. It's very powerful, of course, but it does have certain limitations. And so just to recap these two limitations, it may not terminate, and also it cannot check all the instances. And I argue that these limitations matter. So just as a quick example, the ePaxos specification was published with a bug in it, despite having a formal TLA plus specification. So full verification really does matter. So just to make things a little bit more concrete, let's just consider a small specification that has one state variable, and in the initial state, x is equal to 0. And if we hand this to TLC, it will start to expand the state space. So this toy protocol non-deterministically increments x by 2 or 4. And the key safety property here is going to be that x should never reach the state, we should never reach the state where x is equal to 9. And if you use TLC to model check, you're going to be waiting forever because there's an infinite number of states here. So we need a more powerful method. And the more powerful method that we have is called proof by inductive invariance. So an inductive invariant is a formula represented by inv here. It's a first order logic formula, so no temporal operators like a prime or anything like that. And the inductive invariant is going to over approximate the reachable state space of your system, but it should not include bad states like x is equal to 9 here. To be a little bit more formal, an inductive invariant inv satisfies 3 equations. The first equation is called initiation. It says that any state that's an initial state of the system must satisfy the invariant inv. The second equation is called consecution. It says that for any state that satisfies our inductive invariant, if we take a step according to the protocol, then the state will still satisfy our invariant. And finally, safety, which says that our inductive invariant must imply the key safety property of our system. So there's 2 things I want to point out here. The first one is that we only care about safety in this work. And the second one is you can just view this as a proof by mathematical induction, where initiation is the base case and consecution is the inductive step. So going back to our example, an inductive invariant here is the formula x is even. And so we're going to use this inductive invariant for verification, but I'd also like to point out that inductive invariants also provide interesting insights about our protocol. So here it shows us that the state space is even, but for more complex protocols, we're going to get even more interesting insights. So inductive invariants are very powerful, but they're really complex. And so just to give you a flavor for this, consider Mongo static raft. This is a specification for a raft-like protocol that's used in MongoDB. To prove it, it requires 17 conjuncts in the inductive invariant. And it looks something like this big ugly beast here. This is only half of the inductive invariant, in fact. And it takes over 1,500 lines of TLAP's proof code to prove that this is indeed an inductive invariant. So what we really want to do is automate this task. And automated inductive invariant inference is, in fact, the focus of our grant work. This is an important and tough problem, and it's also an active area of research, but it's also a well-studied research problem with many existing approaches. I don't have time to talk about all these approaches here, but I will point out that one of these tools called Endive is an inductive invariant inference tool for TLA+, and we'll talk about this more throughout the talk. There is a problem, though, with these state-of-the-art tools that I just flashed on the previous slide, and it's that they do not scale. One of the key insights in our work here is that all the algorithms for the tools that I showed you, they search for a global inductive invariant. But what we just talked about is that global invariants or really complex for complex specifications. So what we do in this work is we take a divide and conquer approach. And we call our approach fully compositional inductive invariant inference. So I'm now going to give you a high-level flavor for what our approach looks like. It involves 3 steps. So we start with a specification, and we're going to decompose the specification into components, C1 through Cn. We're then going to assign a proof obligation to each of these components. This proof obligation is called an assumed guarantee contract. And then we're going to infer a local inductive invariant that proves that each contract is valid. Finally, the conjunction of all the local invariants is a global inductive invariant that proves the entire system is safe. So the reason why we propose that this solution will work is that each component Cj is simpler than the overall specification. And our conjecture here is that each local invariant is easier to infer than the global invariant. And in fact, we're going to provide some experimental data later in this talk to support this conjecture. Of course, it's great that we have this framework, but we want to automate it. So for step 1, we laid the groundwork for automating this in an FMCAD paper that we had from last year. For step 3, we can actually leverage the state-of-the-art invariant inference tools that already exist to perform local invariant inference for us. That leaves us with step 2 that's not already automated, and this in fact is a novel contribution of our work. So this leads me to our grant results. There's 3 grant results. So the first one is we propose the theory for fully compositional inductive invariant invariance, which leads us to the first divide and conquer framework for invariant inference. Second, we also built Carini. This is a tool that computes assumed guarantee contracts and automates step 2, and it's publicly available on GitHub. And 3, we offer experimental results which demonstrate that our compositional approach can help verification scale to large specifications. So these are the grant results, and this is also going to be the outline for the rest of the talk. I'm going to talk about these 3 things in this order. But before I jump right into it, I'm going to begin by making things a little bit more concrete by introducing a running example. The running example is a toy version of the two-phase commit protocol called toy 2PC. The toy part refers to the fact that we're going to assume that the network is perfect. All right, so the toy 2PC protocol, we have a bunch of resource managers here, and the resource managers are attempting to commit a database transaction. And this whole effort is going to be coordinated by a transaction manager. So if we're going to model this in TLA+, we're going to need a constant, RMs, and we're also going to need some state for the resource managers. So here we have 3 resource managers. They all start in the working state. They're working to commit the database transaction. We're also going to need some state variables for the transaction manager. The key safety property for this protocol is consistency. That says that no 2 resource managers should disagree as to whether the database transaction was committed or aborted. So let's run through an execution of this protocol just to get an idea for what it looks like. We begin in phase 1. And in phase 1, the resource managers attempt to commit this database transaction. So in this case, resource manager R1 is prepared to commit the database transaction. So it sends a prepare message to the transaction manager. Resource managers can also crash, which we model with the action silent abort. But let's assume this didn't happen. Let's assume R3 sent a prepare message, and also that R2 sent a prepare message to the transaction manager. And at this point, the transaction manager is going to realize that all resource managers are prepared to commit. So we enter phase 2 of the protocol, in which the transaction manager decides to commit or to abort. So the transaction manager might send a commit message to R2. A bad execution would be if the resource manager then sent an abort to R3, right? This would violate consistency. So what we really want is a transaction manager to send a commit to all three resource managers or an abort to all three resource managers. Either one will be permissible. All right, so this gives us a flavor for what the TOI2PC protocol looks like. We want to verify TOI2PC now, show it's consistent. So the constant RMs is unbounded, so we need to use the inductive invariant proof method to show that the protocol is safe. So we can use a tool like Endive to come up with an inductive invariant. It looks something like this. And if you squint at this thing, you might notice that you have state variables for the resource manager talking to state variables for the transaction manager. And it's really not clear how we're going to decompose this into local invariants. So this is what I'm going to talk about now. I'm going to show how we can actually verify the TOI2PC protocol using our framework. All right. So step one of our compositional framework is decomposition. We decompose our TOI2PC specification into two components, one representing the transaction manager and one representing the resource managers. And the method of composition we're going to use is parallel composition. Parallel composition is used in process algebras like CSP or the pi calculus, and is specifically intended for distributed systems and concurrent systems. And parallel composition can model both synchronous and asynchronous actions, which is one of the reasons it's so advantageous. So there's 4 actions in the overall protocol here, and you can see that the TM has 3 of them, where the RM has all 4. Why? Because resource managers silently abort without synchronizing with the transaction manager. So a synchronous action here is simply going to be the conjunction of the actions that participate in the action. Whereas an asynchronous action, such as silent abort, will be an interleaving of the asynchronous actions. Just to make this a little bit more concrete, though, I'm going to show you an example of what the prepare action looks like. So here's the specification for TOI2PC, just showing the prepare action. Here's the TM component and the RM component. And what I want you to notice is that the RM component has the resource manager state variables, and it also initializes the state variables and takes transitions in the exact same way as the original specification. And it's also the same with the TM for the transaction manager state variables. And so a really nice thing about having components like this is they cleanly represent the resource managers and the transaction managers. All right, so this is what our components look like. So we've accomplished step 1. So let's move on to step 2. We're going to infer assumed guarantee contracts for these components. But first, what is an assumed guarantee contract? An assumed guarantee contract is for a component C, and the meaning of a contract is that C guarantees gamma under the assumption alpha. So let's make this a little bit more concrete. Let's go back to the original verification problem. We're trying to show that TOI2PC is consistent. But this verification problem is equivalent to showing that TM composed with RM is consistent. This in turn is equivalent to this contract being valid. So this contract says, assuming true, which really means assuming nothing, because true is the weakest possible assumption, assuming true, TM composed with RM guarantees consistency. This in turn is equivalent to these two contracts being valid. So from left to right, the contracts say, assuming true, TM guarantees A, and assuming A, RM guarantees consistent. And these are going to be the contracts that we assign to the components. But now this begs the question, how do we come up with A, right? And this is going to be what our tool Carini does automatically. But for right now, we'll talk about Carini later in this talk. For right now, we're just going to assume that we've run Carini and it comes up with this formula. And this formula, it looks kind of like TLA plus, but it's not quite TLA plus. This is actually a novel logic language we came up as part of this grant work called Symbolic Fluent LTL or SFL. And this is a type of SFL formula called an SFL invariant. SFL invariants contain Boolean value predicates that we see here. And for example, we have the once prepare fluent. Now, this once prepare fluent is true if and only if the resource manager R has sent a prepare message at least once in the past. And similarly for once abort and once commit. All right, so let's talk about what these conjuncts mean. So the first conjunct says that if there's at least one resource manager that has received the commit message, then all resource managers must have sent a prepare message. And if you think about it, this is in essence what's going on in phase 1 of the TOI2PC protocol. So the second conjunct says, if there's at least one resource manager that's received an abort, then no resource manager could have possibly received a commit. In other words, aborts and commits are mutually exclusive. And this, in a nutshell, describes what's going on in phase 2 of the protocol. So now we can see, okay, we're going to use this assumption for verification, but kind of like inductive invariance, we can start to see that assumptions also shed interesting light about our protocol. All right, so we came up with our assumed guarantee contracts. Now it's time to move on to step 3, where we infer local inductive invariance. So these were the 2 contracts we came up with. Our goal is to come up with a local inductive invariance that proves that each contract is true. And so the strategy we're going to take is going to look something like this. And I'll demonstrate with the contract on the left. Okay, so there's 2 steps. The first step is we're going to translate this contract to a TLA plus specification called TM hist. And I'll explain why the underscore hist on the next slide. The second step is we want to find an inductive invariant that proves that TM hist satisfies A. But this is just a usual model checking problem that we can use an off-the-shelf inductive invariant inference tool for, such as Endive. And we're going to take a similar strategy for the contract on the right, but I'll get to that in a minute. For right now, let's focus on the contract on the left. And like I said, we're going to translate this contract to a TLA plus specification. We're going to call it TM hist. And the first thing we're going to do is we're going to copy the contents of TM into the specification. Next, we're going to add some history variables to the specification. So these history variables are why we call the specification TM underscore hist. We're going to add some history variables to the specification that represent the values of the fluents. We're also going to initialize the state variables for the fluents to false. Why false? Well, because at the beginning of the specification, no actions have occurred, right? So once prepared is going to be false. Same with once abort and once commit. And then we're going to add some logic for transitions for our fluents too. So when a prepared action happens for the resource manager RM, we're going to set once prepared for RM to true. We're also not going to change once commit or once abort, but you can imagine when an abort action happens, we'll update once abort to true for the resource manager that receives the abort message. Finally, we're going to translate our assumption, our SFL invariant, to TLA+. And this is a very simple syntactical transformation. We're just going to replace the fluents, the predicates for the fluents, with the state variables that are that hold their value. Then our contract is true if and only if TM hist satisfies A. And so, like I mentioned earlier, this is just a usual model checking problem that we can use Endive for. And if we run Endive on this specification, it comes up with a local invariant that looks like this. And now we can start to get a sense for what a local invariant looks like. You can see that it only refers to the state variables for the transaction manager, not the resource manager. But the way it gets around that is by referring to state variables that represent the actions, in other words, the fluents. So this is how we get locality for our local invariants. Okay, so we proved the contract on the left is valid. Now we're going to examine the contract on the right, and we're going to take a very similar approach. The only difference is that we're now going to, instead of proving A, we're going to assume A and prove consistent. So we're going to translate this to a TLA plus specification, RM hist, and it's going to look very similar to the previous case where we add our state variables that represent the fluents. There's just two differences here. So the first difference is that we're going to assume A holds in the initial state. And then we're going to assume that A holds in the next state of every action. In other words, when we say we assume A in our contract, we're really saying that we assume the invariant. We assume A holds in the initial state and every following state. So that's the meaning of assuming something in a contract. And then RM hist, this contract is equivalent to saying that RM hist satisfies consistency. And of course, this is a usual model checking problem that we can use endive for. And if we pass this to endive, it gives us this local invariant. Okay, so we proved both contracts are true by coming up with local inductive invariants, which means that we can move on to global safety. Global safety is very simple. We just take the local invariants that we just came up with, and we take the conjunction of them. And this notation here means that inv, the conjunction of the local invariants, is a global inductive invariant for the entire toy 2PC system. Okay, there's a lot going on here, so I'll just recap very quickly. The first step of our compositional framework is we decompose into components. Step 2 is we infer contracts. Step 3 is we come up with a local invariant for each contract. And then finally, the conjunction of all local invariants proves global safety. So as promised, I want to talk now about automated assumption inference. So automated assumption inference is our answer to automating step 2 of this pipeline. And we're faced with this question. How do we find the assumption A? This, of course, is known as assumption inference. And our solution is going to be based on a type of learning called counterexample guided inductive synthesis, or CGIS learning. For the sake of time, I'm just going to give a high-level overview of the algorithm. I have some examples that I'm going to skip, but I can go over them later if people are interested. So our algorithm is going to begin by initializing our assumption to true. And then we're going to enter a loop. And the first thing we're going to do is we're going to check, is A strong enough for RM to guarantee consistency? And we're going to get a counterexample trace T. If T is empty, then it means that, yes, A is strong enough for RM to guarantee consistency, and we'll return the assumption. We're done. If it's not empty, it means we have a counterexample. And what we do is we come up with a blocking invariant. So this is an SFL invariant that eliminates T, doesn't allow the trace T to happen. And we call this, this formula B, and we add B to the assumption. And we just continue in this loop until A becomes strong enough in order for RM to guarantee consistency. This blocking inv routine is really what makes this a CGIS style algorithm, because it generalizes from a counterexample, from a concrete trace to a symbolic formula. And we implement this as a constrained LTL learning problem, which is based on our work from ICSI actually earlier this year. We do include 2 novel extensions to this work as part of this grant to include quantifiers and fluents in order to synthesize SFL invariants. I do want to point out that this scheme easily generalizes to multiple assumptions. So here I'm showing actually the full 2-phase commit protocol. The full two-phase commit protocol does not assume a perfect network. It has the network represented by the component env. And in this case, we need to, since we have three components, now not two, we need to find two assumptions. So we need to find A1 and we need to find A2. And the way we're going to do this is in two steps. So step one, we're going to combine the TM and env component into one contract. And we'll run our tool Carini to find A2. And now, once we've found A2, in the second step, we can infer A1 because we already have A2. And so in general, you're going to run Carini once per assumption that you need to infer. So here we run it twice because there's two assumptions we want to infer. Our tool Carini implements this algorithm I talked about. It's a command line interface tool that's available on GitHub. And I just want to point out it automatically creates the HIST files for you for convenience. I'm now going to move on to our case studies and experiments. And I'm going to begin by just giving an overview of our experiments and our key findings. So we have three case studies. The first case study is a smaller case study. It's the two-phase commit protocol. And compositional inference was slower, which suggests that compositional inference may have more overhead than needed for small specifications. So we tried our compositional verification framework on a bigger case study. And so this is case study 2, and we actually found that compositional inference is more efficient in this case than the global approach. Our third case study is our largest case study. In fact, this is the Mongo static raft protocol that I talked about at the beginning of this talk. This is a real-world specification that the global approach does not work for, NDI fails, but using our compositional approach, we were able to verify this protocol semi-automatically. And what we notice throughout these case studies is that the artifacts of compositional inference, so assumptions and local invariants, they provide additional insights beyond the global invariant. Okay, so for our first case study, this is the full two-phase commit protocol. It has three components, as I mentioned a little bit earlier. We're going to add up the time it takes for us to compute an inductive invariant compositionally. Step one, decomposition is instant, so I don't include it in the time. It's negligible in every case. So we run Carini to synthesize contracts. So Carini takes 61 seconds to come up with A2, a little over 2 minutes to synthesize A1. And to come up with the overall time, we're going to add these times together because we run Carini serially. However, we use Endive to come up with the local inductive invariants. And I can't see the time it takes right now because the Zoom control panels are in front of my screen. So I don't know how to collapse it. So you can all see how long it takes yourselves. But what I will mention is that we are going to calculate the overall time right now, not by adding the times up for local invariant inference, but by taking the max. And the reason is because local invariant inference can be done in parallel. Each individual contract is an independent proof obligation, so this step can be parallelized. This leaves us with a total compositional time of a little over 3.5 minutes, which is slower than the global approach with Endive, which takes about 35 seconds. So this shows us that there is an overhead to our compositional approach, and for small protocols, it may not be worth it. So we apply our approach to a larger protocol, a database server, where there's two components. It takes Carini 15 minutes to infer the contract. And again, I can't see how long it takes for it to infer the local invariants, but the overall time is 24 minutes, which is much more efficient than the global approach, which takes 1 hour and 22 minutes with Endive. So this shows us that our compositional verification framework actually can be far more efficient than the global approach when it comes to finding an inductive invariant. Our third case study, Mongo static raft, has three components. So from the bottom to the top, we have one that represents the commits, the logs, and the metadata. So the metadata is going to include the leader, who's the leader right now, stuff like that, for those of you who are familiar with Raft. And Carini will take 19 minutes for inferring the first assumption, and it takes 1 hour and 39 minutes for the second assumption. It takes, I believe it's 1 minute for inferring the local inductive invariant for the first component, but the other two components NDI fails to complete for local invariant inference. So we had to come up with these inductive invariants manually. So overall, this leaves us with just under 2 hours of compute time plus some manual work to come up with the local invariants for the metadata and the log components. In contrast to NDive, which just completely failed for the global task, and we had to come up with an inductive invariant manually. So I'd like to talk a little bit more about this. So I'd first like to point out that this case study is beyond the reach of all existing inductive invariant inference algorithms. Using our compositional approach, though, we're able to infer an inductive invariant semi-automatically. And I'd like to talk a little bit about what the local invariants look like in terms of their size. So if we count the number of conjuncts as a rough approximation for how big these inductive invariants are, you'll recall that the global invariant for Mongo static Raft involves 17 conjuncts, whereas the components, the local invariants, involve at most 9 conjuncts. And the complexity of an invariant increases non-linearly with the number of conjuncts. So having at most 9 conjuncts is a big improvement over the 17. And we also notice that we gain efficiency in terms of the proof size. So it takes over 1,500 lines of TLAP's code written by a human to prove, whereas it's under 200 lines of TLAP's code to prove that the local invariants are correct. So this is a huge efficiency gain. I also would like to offer some interesting insights we noticed while verifying Mongo static Raft. So A2 is the assumption for the log component, and one of the conjuncts for the assumption A2 is an SFL invariant that looks like this. And it says that if you have a server S1, that's a leader at term T, and if you also have a server S2, that's also a leader at term T, then S1 and S2 must be the same server. And for anyone who's familiar with Raft, you might recognize this invariant as the 1 leader per term lemma that is key for proving that the Raft protocol is correct. And Carini came up with this invariant all on its own. And we believe that this is part of the reason why our compositional framework makes local invariant inference simpler, is because it offloads some of the burden of coming up with key invariants to assumption inference. Furthermore, I'd like to talk about one of the local invariants, the invariant for the log component. And this conjunct, this is one of the conjuncts in the local invariant, it specifies when an entry must be in a log. In fact, this is the only conjunct that specifies when an entry must be in a log, compared with the global approach that has this conjunct that specifies when an entry must be in a log. And you can see it's much bigger and more complex. And we found that this conjunct actually over-constrains when an entry must be in a log. And the reason we were able to come up with such a concise conjunct for when an entry must be in a log using the local approach is because we didn't have to worry about complex interactions of variables that are across different components. So this led to a more concise encoding of this invariant. Okay, so I'd now like to wrap up by talking about some future work. The ultimate vision is to have fully automated, fully compositional inductive invariant inference. And so to do this, we're going to need more automation. So we need more automation for decomposition. basically right now, the tool that we use, it works for small specifications, but we want to extend it to more complicated ones. For example, it doesn't work for Mongo static graph, but it does work for the first 2 case studies. And also, NDive does require some manual work, so it'd be great to fully automate this, as well as we'd like to improve even our tool Carini. We'd also like to investigate more granular decompositions. You may have guessed, but the maximum number of components is going to be the number of state variables in your specification. But we'd like to see whether it's possible to make even more granular decompositions with more components. On a more theoretical note, we want to investigate the expressiveness of SFL invariants. This will help us figure out whether there's assumptions that cannot be expressed as SFL invariants, may help us prove completeness theorems. And we'd also like to apply our approach to more case studies. There's also some other extensions we envision, such as extending our assumption inference algorithm to liveness properties. A particular wish list item I have is that TLC would support the parallel composition operator. That would be great. And finally, something I'm particularly excited about is weakest assumption calculation. So we talked about assumption inference with Carini, but we're interested in coming up with the weakest assumption, the most permissive assumption. This has the potential to speed up assumption inference, but it also has the potential for us to create a new model checker for TLA+. And I'm just going to spend a tiny bit more time talking about what this would look like. So in the context of the full 2-phase commit protocol, remember there's 3 components, the TM and the RM for the system plus the network. The weakest assumption of the system with respect to consistency is going to be the most permissive network such that the system can guarantee consistency. And we can actually already approximate this using Carini. Carini comes up with a formula that looks like this. This basically says that if a resource manager receives a prepare message, then a prepare message must have been sent. This shows us that messages can't be forged is basically the requirement, but you can have duplicates and drop messages. But we don't know if this is the weakest assumption. It'll be interesting to calculate the weakest possible assumption. So you can imagine a model checker for TLA+. Basically, this is the current paradigm. The current paradigm is a binary question. Is your system safe? Well, without the network assumption, no. And with the network assumption, yes. But the new paradigm would go a step further. It would tell you yes or no, but in addition to telling you no, it would also give you the most permissive assumption such that you would guarantee correctness. It would give you an extra layer of information. The assumption may look like this, it may not. More research is necessary to tell. Anyway, so that's the end of my talk. Thank you all for listening. Now ready for questions.
Yeah,
Thank you
so
for the
thanks a
virtual.
lot. Marcus, do you want to start, or does somebody else want to start? I'd have a few questions as well. Okay, I'll just fire off. So the first step in your pipe. So I think basically what you presented makes a lot of sense, right? So this decomposition. So you can reasonably hope that local invariant inference becomes much easier than global invariant inference. And this way of adding history variables, I mean, that also resonates with, I guess, with people who have done invariant proofs. So the first step in your pipeline is this decomposition step where you take your system apart, so to say. And I wasn't quite sure and I understood how you do that. So is there some guidance on how you decompose, how you find the components?
Right now, we don't have guidance on it. So we do have a tool that does this automatically. This is from our FMCAD work from last year. But like I said, it doesn't work on more complicated specifications. Perhaps the best thing I can do is show you the example, maybe again. I don't know if this is going to help answer your question or not, but It works. Okay, it works best when your specification is in disjunctive normal form. In this case, it's simple to automate because you can see here the prepare message, or the prepare action is just the conjunction of the two components actions here. So how would you break it up? Maybe you have some human intuition about, you know that the transaction manager is separate from the resource manager. It might give you an idea about how to break it up. Sometimes the best decompositions are actually very non-obvious, and it's still an open research question about how to find the best one. Some human guidance would be really awesome, but that still is a research question that would need to be addressed.
Yeah, great talk. I have a follow-up question to what Stefan just asked. So this is about breaking up a specification into multiple components. Could you also use your work to take two specifications of different systems and combine them and then learn something about them? So where you sort of start from individual components and you, for some reason, want to combine those systems. Perhaps you have a larger system and parts of it have been specified, and now you want to put those specs together.
Absolutely.
Good.
Yeah, absolutely. Right now, we assume that the method of composition is parallel composition because we're going to infer an assumption that's in the shared alphabet between the components. So in this case, the shared alphabet is going to be prepare, commit, abort. It's not going to include silent abort, right? Silent abort, we don't want to be part of the assumptions. So it is important to have your components that you pass through it be composed with parallel composition. But yeah, that's totally a workflow you could do.
Thanks.
Okay, maybe a second question I had was, so if I understand correctly, basically what you're assuming that you get is a chain of assumptions, right? You have your different components, and the first one has no assumptions, so you simply have true. The final one has your overall property, and the others are somehow in between. So is that always the case, or could it happen that you have components that mutually depend on each other?
I love this question. This deserves a very long answer, so I'll try to keep it concise. Yeah, so
Sorry.
you completely identified that the style of compositional proof we're using is transitive. We require an assumption to be a guarantee and a assumption of adjacent contracts. And so in general, yes, I think we'll probably need to extend this work to more complicated proof techniques such as circular composition, which is something that's been done for finite systems but not parameterized systems. So that is certainly future work. But this method is actually more expressive than you would expect. And using this method to verify Mongo static graph actually kind of solidified this for me in my mind. Because it seems like, yes, it's transitive. And so if you have, okay, Mongo static graph, right? You have a bunch of nodes in a cluster. It seems like all these nodes are dependent on each other's actions. You should need to use circular composition. But the thing is, we're following this natural decomposition into variables given by TLA plus. So TLA plus actually helps us have a really kind of weird decomposition into components that's not by the nodes, but it's by different areas of the protocol. So the transitive proof method is actually more applicable than you'd think. It's basically our assumptions now talk about assumptions based on the metadata. So we get like 1 liter per term, for example, versus a different decomposition based on the nodes where you would need information circularly if you took that decomposition.
Okay, makes sense. So, I mean, that's also one of the claims of the RAF paper, that you decompose the problem into separate subproblems, and one builds upon the other, right? So you start with lead election and so on.
Yeah,
so by the way,
totally.
add just a detail. In Mongo static raft, do you assume that leader election is atomic or not?
Yes, yeah. Leader election, we do. Yeah, I don't have a specification. But yeah. We assume that leader election is atomic. It takes the quorum and um it advances the state of all the nodes in the quorum at the same time.
Okay. Yeah, I'm just asking because I also played a little bit with raft and I also had a specification where leader election was atomic, and that made the inductive invariant much easier. So you see in raft there's this proviso that in the raft paper they introduce towards the end where they say, oh, for leader election we have to have a stronger guard because otherwise it breaks. And that's related basically to the more difficult invariant that you get.
Yeah, I definitely have the full wrap protocol somewhere in my sights. I would love to tackle that. It's big, right? It would be very interesting to verify it compositionally though. And I think it would be a really awesome use case for this framework.
Okay, and while I have the floor, I'll ask my another question. So about your fluent language. So if I understand correctly, I mean, this is a full-blown temporal logic,
Yeah.
but you only use invariants, right?
Yeah. This is an interesting observation. We defined it as a full-blown temporal logic. Let's see. But we only use invariants here. So basically what I'm envisioning is we can use we can maybe use temporal operators on for if we try to tackle liveness properties. So right now it's just an implicit G in front, so we don't bother showing that with the TLA plus convention. But in the future, we hope that we can use the full logic for inferring assumptions for liveness properties. Yeah, here we go. Here's the assumption.
Okay, I see. So I was just wondering if, I mean, for what you need here, you could actually have stayed within TLA plus and somehow introduced the history variables just at the TLA level without switching to a different formalism.
Yeah, that's true. Okay. It's totally possible to just introduce this as far as history variables. And that's actually how this whole thing started. It started with basically history variables. The thing is, at the very least, these fluents recognize an interesting pattern, and the pattern being that these history variables should represent actions. The fact that they represent actions helped us to come up with these formulas manually at first. But at even more so, one of the advantages to making this a full-blown language where we have fluents is this actually helped us to come up with the invariant inference algorithm. We literally use action-based traces as part of our constrained LTL inference problem to come up with action-based formulas. So the action-based semantics are actually very important for coming up with for automation, basically.
Yep, makes sense. Thanks. I'll leave the floor to others.
I have one. You mentioned that you want the compositional operator to be implemented in TLC. Have you looked at it? And if yes, what are your observations? What would that entail?
We briefly actually tried to implement it ourselves a couple of summers ago, and yeah, it's a little tougher than you'd think because of quantification over any sets. Basically, if you were to just handle actions with no parameters and without quantifications, yeah, it's just as simple as taking the conjunction, right? But if you're going to implement parallel composition for any kind of specification with quantifiers, I think probably the way I would imagine to do it is you need to assume that you have the same quantifier structure between the two components. So, it's a little bit rigid. Maybe there's ways to extend it, but if you had the exact same quantifier structure, here, let me just go back a couple slides. Let's see. Oh, well, I'm not showing it exactly. Basically the next definition is the disjunction of actions. If you have the exact same next definition as the disjunction of actions, you could imagine that combining everything wouldn't be so complicated. I don't know if that's a satisfactory answer, but
Thank you.
I have a question, if I may. So you have this parallel composition operator, and it looks like it is symmetric, right?
yes.
Uh,
Yeah, it's
and
commutative.
yeah. So when you kind of derive assumptions, you use specific order between these components. So the question about this order, does it matter? And does your tool kind of help to identify this specific order?
Yeah, that's a great question. So you're right. The order certainly does matter. That's one of the reasons why decomposition can be such a tough problem. The order is sort of for two components. It's sort of fixed in the sense that, let's see, maybe I can go to contract here. It's sort of fixed in the sense that for these two contracts, you'll notice that the property consistent only makes sense in the context of RM, not in TM. So in this sense, the final component is fixed, right? It's whatever component whose state variables are referred to from the safety property. When there's multiple components, though, the order for the first n-1, it's not clear how to order them. And so how might you go about figuring out an order? Sometimes human intuition helps. To give a more precise answer, in our FMCAD work from last year, we actually came up with a partial order we call the data flow partial order that helped us to order the components, helped us to group and order the components, and it did give us some success in figuring out an order.
Okay, so thank you. So basically, you're saying that it's up to it's up to author, right, to come up with a specific order and then try to apply this tooling.
Yeah, it's up to the author, but we do have a tool that at least attempts to automate this.
Okay, I got it. Thank you.
More questions?
I have one. This is Chris. Thank you, Ian. This was great. My question will betray my ignorance of temporal logic, but it goes back to Stefan's question. I'm still not quite seeing, perhaps I need to read the paper. I'm still not quite seeing why you needed to invent SFL and why using, say, RTLA, the underlying one of the underlying layers of TLA wouldn't have been sufficient.
Yeah, it's basically, in the strictest sense, it's not necessary. Maybe it's best to think about it as a theoretical convenience. In practice, like I said, it does help with synthesis. But in the strictest sense, you are correct. It's not necessary. So basically, here, maybe we can go back to here.
I'm just wondering if the inference rules, is it because the inference rules are simpler in some way, so they're more amenable to automated manipulation, or what is it about RTLA that meant you decided that you needed a different logic?
Yeah, it makes the inference rules simpler for sure. Basically, the inference rules, you don't have to worry about auxiliary or history variables in them, so it makes things less clunky. With the action-based language, the auxiliary variables are automatically, they come automatically, right? All you have to do is come up with the fluent, and instead of inventing auxiliary variables. So with auxiliary variables, basically the insights you need are fluents. So it's kind of like a clean way to wrap things up, and it just happens to be very useful for automation as well. But I think your intuition is spot on. You could totally just use auxiliary variables in a technical sense.
Okay, thanks. Is there more on it in the paper? Does the paper have the details of SFL, the language, the inference rules, etc.?
Yes, exactly. Right. I don't want to put a link to it in the paper just because for the next until this weekend it's still under review technically. But if you go to my website and you see the paper, we talk about the framework as a two-layered framework. Basically, the action layers are at the top. We talk about action-based semantics, and it explains parallel composition because process algebras are usually with action-based semantics. And then you go a step below, layer number 2, you get state-based things. And this is how, of course, you get local invariants. So yeah, and you'll even see we progress through the different rules. We start off with the state-based rules, which look clunky, and then you get nicer action-based rules.
Okay, thank you. I'll take a look.
Awesome. Yeah, thank you.
Can I also join the Q&A? I was just looking at USFL rules in the archive paper. So, is it correct to say that this approach somehow works because you have somewhat monotonic behavior? Basically, you send a message, you receive it, and you don't forget that you have received it.
Yeah, this is a good point. This kind of goes back to Stefan's point earlier about do you need circular rules? And so yeah, there is some sort of monotonicity. And so the first protocol I tried this on was Toy2PC, and I thought maybe it won't work for anything else. And so applying it to Mongo static graph definitely gave me the insight that the monotonicity is more permissive than you'd expect, right? You can have monotonicity in parts of the algorithm that you didn't expect. So the monotonicity in Mongo static graph, or at least part of it, is relying on leader election theorems, such as leader completeness. And so in that case, you actually don't need circular composition for that.
Right. So there are some protocols where components forget about messages, like do some kind of garbage collection, you know?
Mm-hmm.
Would this work? I'm just guessing. I'm not like.
Yeah, no, it's a great question. I think in that case you'd have to decompose along some other something else besides the message forgetting, right? You need to decompose along some other line that is transitive. And if you don't have that, then this technique won't apply. But what I will say is that if your protocol gets big enough, at some point you're probably going to have some sort of transitive dependency, right? Is that always the case? I don't think I want to claim that, but I think the protocols I've seen, if when they get big enough, that's usually the case. But nonetheless, I still do believe that we should look into extending this to other types of proof rules like circular proof rules.
Yeah, thanks a lot.
Okay. So it looks like an hour was just about right.
I have one last question.
Please go ahead, Chris.
I'm wondering when you inferred the local hopefully inductive invariance, do you have a soundness check? Do you use another tool like Appalachia or TLA Plus with the probabilistic approach to check that they're inductive before you start doing the proofs?
Yeah. Yeah. So first of all, yeah, the local invariants are definitely inductive. That's a key requirement. And yeah, this
I
we
know,
do.
I realize that they have to be. I'm just wondering, just in case
Yeah.
you have, are you still checking them via some other tool before you try and do the proofs, or do you believe um, that the inference mechanism is completely sound and bug-free, so you just don't need to bother? You would catch it in the proof, right? You wouldn't be able to prove it if it you
Right.
wouldn't. But I'm just wondering if you have linked into your automated tool chain an inductive invariance checking step, because I believe that Appalachia can do that. But I've never used Appalachia, but
I've
right,
never used
Igor?
Appalachia either, but I was under the impression that it did the check for finite instances, or even is that not true?
Yeah, it's true. If you
Okay.
have like unbounded data structures, cannot do much. Yeah.
Yeah, so we read a T-Labs proof as you were saying, and yes, when I did these, I took the strategy of uh, using the probabilistic method. I assume we're talking about the same thing where you use TLC to generate random states, and you check to see if a step from those states is inductive. So yeah, I use that exact approach. It is actually a little bit interesting. I'll comment on this. It doesn't work quite as well as you'd hope when you start to augment your specification with auxiliary variables, because now you're adding a lot of variables, and your state space, that your non-reachable state space, can actually blow up. So it actually requires you to write like a bash script and just repeat these things. So it's certainly the probabilistic method has its trade-offs, but I see this as a little orthogonal to the framework here, right? Because that's under the umbrella of local invariant inference, which we kind of treat as a black box, right? It's you we say you can use any off-the-shelf tool for it. So NDive gives you probabilistic. It says this is most likely an invariant, but you could imagine in the future there'll be another tool that says this is definitely invariant, and here's your proof for it. So I see this as kind of independent to the framework we have.
Got it. Thank you.
And thanks for the question.
Okay. So yeah, thanks again. Great talk and great work. Thanks a lot.
Thank you. I appreciate all the
Yeah.
questions and everyone attending.
Thank you for doing it. I'm glad the foundation was able to help with the grant. Thank you very much.
Okay, so see you probably at the next community meeting, probably in a week or so.
That's good.
See you then. Bye-bye.
Thank
Bye-bye,
you.
everyone.
Bye.